What's going on, everybody? Here is your solution video for the practice projectile motion worksheet. So we go ahead and start with number 1 here. Dropping a baseball and we're shooting a cannonball. So for the interest of math, where it says negative 9.8 meters per second, I will be using negative 10 meters per second squared. And we have a cannonball that is launched with a horizontal speed of 20 meters per second. So right away, we'll go over to the cannonball side, and we'll do the same time. We have 0, 1, 2, 3, 4, and 5. So because this cannonball is launched with a horizontal speed of 20 meters per second, that means that every second it will travel 20 meters. So at time 0, it has an x position of 0. It is now in 1 second traveled 20 meters. So that means that at 2 seconds it's traveled 40, at 3 seconds it's traveled 60, 4 it's at 80, and at 5 seconds it has already traveled 100 meters. Now if we want to get into the y position of the cannonball, so at time 0, according to the graph, we start at an initial position of 0. So this way, we know we're starting at 0. After 1 second, we're going to now be using our kinematic equation. Y, our position, equals the initial position plus the initial velocity in y times time, plus 1/2 the acceleration times the square of the time. Because our initial position is 0, that term is 0. Our initial velocity in y is 0, that goes to 0. So now the position of this cannonball in y is solely dependent on the acceleration times the square of the time divided by 2. A is our gravity now, so that's negative 10 meters per second squared. T will be our time. So after 1 second, we will have 1/2 times negative 10 meters per second times 1 second. So this will end up being at a position of 5 meters. 5 meters. After 2 seconds, we will now have 1/2 times the gravity, which is negative 10, and then we will multiply that by 2 seconds squared. And now this object will be at 20 meters. As we keep on moving, we'll now do 1/2 AT squared continuously here. So at 3 seconds, we're at a position of 45 meters. At 4 seconds, we are at 80 meters. And at 5 seconds, we are at 125 meters. And we would consider all of those to technically be negative based on how we've been doing things in class, with up being positive, down being negative. But based on the scale of this graph, it's just considering this height to be 125 meters. For the baseball, we will use that same kinematic equation, and again, our initial position is 0, our initial velocity in y is 0, so we just focus on the 1/2 AT squared. So the initial position is 0. After 1 second, it's at a position of 5 meters. After 2 seconds, 20. 3 seconds, we're at 45 meters. At 4 seconds, we're at 80. And at 5 seconds, we are again at 125 meters. So very, very conveniently, these objects are falling at the same rate. So if we draw it, and it's a real rough estimate, just drawing the dots for where it has fallen. And this is put on these diagrams. And now when we're doing the cannonball, we have to then keep in mind the x and the y components here. So where this object hasn't fallen very much after the first second, after 2 seconds it begins to fall more substantially. 3 seconds, it's really starting to go down, and so on until it hits the ground in a nice parabolic curve, a nice quadratic function. So which two hit the ground first? They hit at the same time. They hit at the same time. So now comparing the two diagrams, the vertical free fall motion and then the two-dimension free fall, the effect on an object's horizontal motion upon its vertical motion doesn't matter. Does not matter. The vertical motion is only going to have that force due to gravity pulling it down. Otherwise, there's no other forces acting on it, so the horizontal motion doesn't really have an impact on the vertical motion. On to page 2, where we'll again be using the same initial x velocity as we were just using on the first page. So again, we're given this nice parabolic curve of the ball falling through the air after being launched. And because this is the same problem as before, the total displacement in x, we said, was 100 meters, according to the first part. So our displacement in x, I don't know why I'm writing a 2, it is 100 meters from the origin. And we are 125 meters for our displacement in y, for the height of this cliff. Number 6, the ball being launched with an initial velocity of 20 meters per second. So now we're looking at the velocity vectors here. So just what the velocities are at these moments in time. We know that the velocity in x never changes. So all of these, the velocity in x, they're all 20 meters per second. And that velocity does not change. That velocity does not change because there's no forces acting on it in the x direction. So now our velocity in y, after 1 second, has become negative 10 meters per second. After 2 seconds, we're at negative 20 meters per second. 3 seconds, negative 30 meters per second. And at 4 seconds, it is at negative 40 meters per second. Because this object changes at negative 10 meters per second each second. So at 1 second, negative 10. After 2 seconds, negative 20. 3 seconds, negative 30. And 4 seconds, negative 40. So if the ball in this diagram has struck the ground after 4 seconds, how high was the cliff? And then how far from the base of the cliff will it land? So how far from the base of the cliff? We'll go ahead and do part B because that one is a little bit easier to do. This object travels 20 meters per second in the x direction, and it has traveled for 4 seconds. So we can do our position in x equals our velocity times our time plus the initial position. Well, our initial position, we can go ahead and call that 0, so that will cancel. And now when we plug in our terms, we have that our position, and that is our initial velocity, so we have 20 meters per second times 4 seconds, and we will get 80 meters for part B. So part A, how high is the cliff? So if we want to take a look at how high this cliff is, that's going to be our kinematic. That will be our kinematic equation again. Our y equals, I'll use a different color. That will be our y equals y0 plus the initial velocity in y times time plus 1/2 acceleration time squared. Those first two terms are 0, our initial position is 0, and our initial velocity is 0 in y. So that means that we're just concerned with the 1/2 at squared. Our acceleration is -10 meters per second per second. We will multiply that by the 4 seconds that it fell for, and then divide that by 2. So this object has fallen 20 meters. And actually, I made a mistake there. It is not -20 meters because we need to square our time. So we need to square that 4. So we get -10 times 16 divided by 2. So this has a height. The height of this cliff is 80 meters. 80 meters. If the initial speed was 16 meters per second, how far away from the cliff will it land? So this one, again, our initial position is 0. We'll take 16 meters per second, multiply it by 4 seconds to get 64 meters from the cliff. Number 9, we're going to use this diagram to draw the free body diagram for a projectile as it rises towards its peak, at its peak, and falls. So 9 and 10, these are all after it has left the person's hand, the cannon, and before it has come in contact with anything else. So our force diagrams here, we have the force due to gravity on all 3 of them. And that is it. That is the only force present. And when it's launched at an angle, does not matter. An angle does not impact the forces present when it becomes a projectile. Because a projectile means that it is in free fall motion, and that free fall motion means that the only force acting on it is the force due to gravity. And now this last one, we have a projectile launched with a speed of 31 meters per second at an angle. We're given the velocity in x and the velocity in y, and then we want to know what the accelerations are in each direction. So we know right away, once it leaves, it becomes a projectile. The velocity in x remains the same. So these, all of them, become 10 meters per second. So our acceleration in x is always 0 meters per second per second. Always. Our acceleration in y always be -10 meters per second squared. Those are all the same. Now our velocity in y will change at -10 meters per second each second. So after 1 second, it's traveling 19.4 meters per second. After 2 seconds, it is traveling 9.4 meters per second. At 3 seconds, this will be traveling at -0.6 meters per second. At 4 seconds, -10.6. At 5 seconds, -20.6, and at 6 seconds, -30, -30.6. And again, all of these are using -10 as the acceleration. Had you used -9.8, you would have gotten a slightly different number. So there's your projectile motion practice. Again, most of it conceptual. Tried to keep the calculations to a minimum. We will see you guys in class. I hope you guys enjoyed the video.